Okay. Left a letter out of decay there, kind of slipped it in, it might be hard to read. Exponential growth or decay. The equation is always, until it gets modified, of course. And often we're talking about something that grows or decays in time. So I'll use t for the variable rather than for the independent variable rather than x. dy dt equals ky. And I'm going to say k is a positive or negative constant. So y changes at a rate proportional to itself. Okay, what sort of things change at a rate proportional to themselves? A bank account at constant interest rate. And I guess I better say compounded interest. I mean, you put money into a bank account, it's always compounded. There are situations where you could have an investment that just pays straight interest. But we're assuming it's compounded. If you're compounding your money, that means that the interest rate keeps applying to more and more money. So the more money you have, the more interest you're going to get. So that your money grows at a rate proportional to how much money you have in the account. Now, implicitly, this is a bank account where you don't put any money in or take any money out. So you're not tampering with the account. You put it in there, you get the interest, and then when there's whatever amount of money you want to have that hopefully beats inflation so you can reach your goals, you take the money out and use it or do something else with it. Okay, well, that's a bank account at fixed interest. Population that growing without restriction. Okay, well, the more critters you got, the more they're going to produce. No restriction. Okay, now, very few populations grow in this manner. You know, I think I've used guppies as an example because you can look at a tank full of guppies and see that there are a whole lot of them there. And eventually they get crowded and eat the young and so forth. You know, one guppy lays enough eggs that if they reproduce without restriction, they'd probably fill the ocean head to tail within a year. Not that guppies live in salt water, but you get the idea. So, you know, eventually you have restrictions, and those are very soon you end up getting into restrictions. Okay, And that's just one example. You can think through other examples. Okay, so anyhow, population growing without restriction. Let's see, another example. Radioactive decay. You start with a radioactive element. After, say, years, some of it's decayed, so that if you measure the activity with a Geiger counter or something, there's going to be less of it there. So the activity decreases at a rate proportional to how much you have. A little more. Every atom in that original sample has a certain probability of decaying within the next nanosecond, or whatever. And within a year, or after one decays, then there are fewer of them to decay, and then the next one takes, on the average, statistically, a little longer to decay. And of course, in any time interval, the fewer you got, the lower the probability of a decay, and the rate of decay is then proportional to how much you have. I could expand on that idea, but that gives you a general feel for it. And it's a fairly obvious concept. Okay, the more you got, the more activity you're going to have, meaning the more of them are removed from the sample. Okay, they don't go anywhere. They change into something that's not radioactive anymore, presumably. And actually, some elements decay into other radioactive elements with different decay rates. And it all gets kind of confusing, but not confusing, but complicated. You can still set it up with differential equations, that it's going to be systems of equations in that case. So we're not going to go there right now. We're just going to use simple radioactive decay. So those are three examples. In every case, the rate of change is some fixed number times how much you've got. For interest, it's just basically your interest rate. Population growth, well, that just depends on how frequently well, let's say the probability that any female in the population will produce an offspring or some number of offspring. Radioactive decay, as I said, how many, what's the probability that a given particle is going to decay over a certain short time? Okay, and those questions are going to determine K. Okay, well, the solution I should say the general solution, so I'll put the word GEN there. The general solution is always as follows. I'm a little clumsy with my terminology there, but I think the meaning is going to be clear. You're going to get dy over y equals k dt, so that actually the absolute value of y equals kt plus your arbitrary constant. And we've been through this, so I'm not going to. So y equals ae to the kt, where a and k are your parameters. Depending on what kind of information you're given, you might have to determine both a and k. You're not always going to be given the value of k. Now, for example, if you know what k is, and you have some initial condition, then you're going to be able to match that initial condition up here and determine A. I'll do that in a minute. If you don't know A or K, then you have to have two conditions, call them boundary conditions. Okay, you have to know the value of Y at two different values of T. Or possibly, maybe you know Y and Y prime at a given instant. Either way, you're looking at finding a curve in YT space, a function representing a curve. If you know 2 points on the graph, then you got to match up the slope through that initial point, let's say, so that you get the curve that goes through the other point. If you already know the slope, meaning you know Y prime of 0, let's say, so you know the slope here, then that determines everything else. And then you just have to determine one of your constants. Well, let's see how that works. Okay, so let's say we know K and Y of 0. And Y equals e to the kt. So we know all this, we know K. So I'm just going to write this. So if we know Y of 0 and K, well, we're almost done. A is always going to be Y of 0, because if T is 0, e to the kt is 1, so Y has to equal A. So Y of 0 has to equal A, and we've got the value of A, so we have our model. And maybe we know K and Y prime of 0. That is, we know the proportionality constant for our growth rate, and we know how fast it's growing at a given time. Then clearly, Y prime is going to be Ke, Y prime is going to be Ka e to the kt. So again, plugging in 0, e to the kt is going to be 0, going to be 1, kt is going to be 0, e to the kt is going to be 1. So then A is going to be Y prime of 0 over K. Now, if we know K and Y prime of 5, somehow we measured the growth rate at, or the rate of growth, not the growth rate, measured the rate of growth at T equals 5. We didn't measure it at T equals 0. Well, we could reset our clock, okay, to make 5 our 0 point. And so just transform it to just a different t coordinate. But if we don't want to do that, then we might want to just solve this equation. Well, again, we get y prime equals ka e to the kt. So y prime of 5 equals k a e to the 5k. And a then ends up being equal to y prime of 5 over k e to the 5k. Now, all of this is really just one thing. Okay, we just plug in our known information. If it's known information for y, we just plug it in. If it's an initial condition or t equals 0, that makes it particularly easy because the e to the kt is just going to be 1. But if the information is not for a given t, and not for t equals 0, it's no problem. We'll just plug in that information, okay? Just that the e to the kt will now be e to the k, whatever the t was, if we know k. Now, if you don't know k or a, but you know, say y of 0 and y of 5, you know, or y of 5 and y of 9, it wouldn't matter. Except, you know, just a little more, you know, simple algebra step gets us to the solution from what you're going to see here. So we know that you know, y of 0 equals a. Y of 5 is a e to the 5k. So y of 5 equals y of 0 e to the 5k. And e to the 5k then equals y of 5 over y of 0. Now, in general, there are a lot of implications but for the exponential function, given the ratio of two y values. But it really just comes down to what we're doing here. Okay, so five k is the natural log of y of 5 over y of 0. And k equals write it down here because I'm going to need another line anyway. K equals 1/5 the natural log of y of 5 over y of 0. Now, I would normally use an absolute value sign here, but your solution is an exponential function with a constant in front of it. So y of 5 and y of 0 are always both going to either be positive or negative because your exponential function, e to the kt, is always positive. Okay, so depending whether a is positive or negative, both all values of y of t are going to have the same sign. Okay, and then we maybe want to simplify this depending on how we want to interpret our solution, depending on how we want our solution to look. One way of interpreting, of rewriting this, is the natural log of the fifth root of y of 5 minus the natural log of the fifth root of y of 0. Just putting it in one form. And if you don't, you know, if you're a little fuzzy, I don't think you are, but if you're a little fuzzy on the properties of logs, you're going to want to get familiar with them because you use them a lot, as you probably already know because you've already done it. Okay, so that's just another example. Now, if you knew y of 0 and y prime of 0, well, you just get, well, I guess it's worth writing that up because you do get a system of simultaneous equations. So let's say you're given y of 0 and y prime of 0. Then you're going to have two equations. Let's make sure we're low enough here. You're going to have two equations. You're going to have y of 0 equals a. And y prime of 0 equals ka. So that you have a, and then since you have a, you just divide y prime of 0 by k, by a, and you get k. So k is y prime of 0 over a. And of course, that would be y prime of 0 over y of 0. Okay, so there's the process. It's very straightforward. All these equations are solved by pretty much one of these methods. Okay, now we're just going to go on with this survey of the types of models you see in chapter 3, even though, let's see, chapter 3 is going to keep us occupied for the rest of this month. So we have, over the next 2 weeks, we'll do those assignments. Got one due next time, and one due 2 days before the next class, one due in the next class, one due on the last day of the month. And then I will say, we're going to stop and have a test at that point. That'll be right before, well, be a little ways before spring break. So we'll see how we go on. We're going to continue with assignments though. My dates on the assignments look like I don't have them right. We should have an assignment on the 9th, and I'm going to have to adjust the dates in March because I've got 3 dates that correspond to spring break. So it looks like I'm going to be able to move those dates a week later so that we don't overlap spring break. And that's going to give us basically the week before spring break to have the test. Which of course means you can take it pretty much any time before the end of spring break, giving you more flexibility. But in the meantime, we're going to have to do the first 3 sections of chapter 4. Fortunately, those are pretty easy sections. They shouldn't distract you too much from preparation. Anyhow, you're going to have a week of preparation. We can do some more examples and so forth. Okay, well, here we go. Okay, so logistic equation. And I believe we've already talked about this a little bit. The growth rate decreases as we approach a limiting value. And usually this is applied, or typically this is applied to populations. So again, you can think a tank full of guppies. You put a couple of guppies in there, they lay a bunch of eggs, they have a bunch of offspring. Those offspring lay a bunch of eggs and they all mature. And within 2 or 3 cycles of that, it's starting to get crowded. The offspring have less room to hide or avoid being eaten because most fish are cannibalistic, and guppies certainly are. So the growth rate's going to start decreasing. Fewer and fewer of the offspring are going to make it to adulthood. It's getting more crowded too because there's less and less food, so they have a struggle for food, and that interplays. Their offspring are going after food, but that exposes them more to being eaten by the adults, and it gets all complicated and doesn't exactly follow the logistic model, but the logistic model still gives us an overall picture of how the population is going to go, and then we can get into the subtleties of what happens within that population. Okay, so your growth rate decreases as a population okay, growth rate decreases as population approaches a carrying capacity. Now, that's assuming you have the model I've given you where you have an increasing population. You could also put too many guppies in that tank, and then the population would decrease and approach the carrying capacity. So you're always going to get 2 possible solutions. One, if you start below the carrying capacity, one, if you start above the carrying capacity. Okay, so we assume growth rate is proportional to, and I'm going to use P. So the population, and I'll put a P in here. We'll use P instead of Y. Okay, growth rate is proportional to P the population. The more population you have, the more growth you have. And also to L minus P. That's how close you are to the carrying capacity. That's how many you've got. That's how close you are to L. What's happening here is the board is slightly warped. So I'm going to change the direction of the warp. So when I push on it up here, it doesn't pop out down here and fall off. Okay, growth rate, okay, proportional P into L minus P. And I say growth rate, which is a terrible error in terminology. Growth rate is like your value of K. Rate of growth better say rate of change to the population of P. Okay. Growth rate is like your percent interest. Okay. Really talking rate of change of population. That's what Y prime is, of P prime. Okay. Rate of change of P is proportional to P, also to L minus P. So the rate of change, if you understand terminology and the application of proportionality and variation, which it seems like very few people do, even after having covered it. But anyhow, that for some reason, that's a somewhat difficult concept in a, say, pre-calculus class. And it's very mathematically very simple. So not sure where the problem is with that, but it does tend to be a problem. Okay, anyhow, rate of change is then varies SP and L minus P. So you're proportional to P, and also to L minus P, you're proportional to the product of P and L minus P. Now, really, if I use the right terminology, I would say the rate of change of P varies as P and L minus P. But I'm going to stick this terminology I'm using. Maybe for no good reason, I'm going to stick with it. Okay, so I get dp dt is kp times L minus P. General solution, then I'm going to have this. So the integral here is kt plus a constant. You integrate this now by first expressing this as partial fractions. And I'm not going to actually write out the partial fractions, partly because I think I've already done that in this course, partly because I don't want to digress too much into the partial fractions, although I'm not sure this is right. So I'm going to check myself out. There's got to be a negative sign probably here. So I think it's probably going to be this. Now, if we do 1 over P minus 1 over L minus P, well, that's L minus P, 1 over P, minus P over P times L minus P. It's L minus P minus, getting negative signs messed up. P over L minus P plus 1 over L minus P. The minus sign comes in the integration here. Pretty sure that's right. So I'm going to go on with it. And if it's wrong, I'll go back and fix it because it's just a matter of a sign. You can check it out. All we're saying is that 1 over P plus 1 over L minus P equals 1 over P times L minus P. And that's obtained by partial fractions. So I'm not doing that step. So the derivative here is natural log, the integral, natural log of P minus the natural log of L minus P. We're using absolute values now because, of course, L minus P can be negative. You don't really have a negative population, but L minus P can be negative in the case where you start with a population bigger than your carrying capacity. Okay, and then this equals KT plus C. And then, of course, the steps here, and I believe we've been over them previously, just to make sure we remember them. Natural log the absolute value P over L minus P, KT plus C, so that P over L minus P equals E, well, AE to the KT, where A is equal to E to the C, C being an arbitrary constant. And that has to be greater than 0. Now, we're going to actually have the absolute value sign around this. The absolute value of this equals this. But if the absolute value is this, then here P over L minus P is going to be plus or minus this. And this could then be expressed as just P over L minus P equals A e to the KT, where A could be any real number except 0. Then we have to solve this, and I'm out of space down here, so I'll continue over here. So we get just to summarize, we get at least that much on the board. Now, the only difference between what I wrote previously and what I've got here is I don't no longer have the plus or minus with A being greater than 0. A plus or minus A, where A is greater than 0, is either greater than 0 or less than 0, can never be 0. Of course, if it was 0, you'd have a very uninteresting model anyway. Okay, so P over L minus P equals this. And this is just algebra. Okay, there's no real differential equations to it. After you do the integration, but rearrange the thing and then start integrating, you're just into calculus and then algebra. You get P equals L minus P A e to the KT. So that, abbreviating the algebra some because I'm sure that we've done this. Use the distributive law here. And now we can solve for P. Now I'll write out the step. And A came out kind of bad. That's on the board or something. Chalk out of it. P. Then factors out here. And I don't want to take up board space with another line. I've got plenty of space over here. You get P equals LA e to the KT over 1 plus A e to the KT. Now we got that constant A here and here, and we really kind of want it someplace where we can deal with it. So I'm going to divide both numerator and denominator by A e to the KT. So P equals L divided by actually, I'm just going to divide by e to the KT because I'm going to end up, actually I want to end up with reciprocal A in the denominator. It's just a matter of taste. Okay, if I divide by A e to the KT, then I'm not going to have an A up here. I'll get rid of this A here, but I'll have a 1 over A here. We've got a 1 over A here. I'm going to write it both ways. Okay, you're going to get 1 over A e to the negative KT plus 1 or LA over e to the negative KT plus A. You can read these forms. I kind of like this form, even though you get that reciprocal, you got to be careful with it. And it's a complex fraction the way you've written it out there. But what this is telling you is as t approaches infinity, this 1 over A e to the negative KT approaches 0. And the denominator approaches 1, so that P approaches L. Your population clearly approaches your limiting population. In this form, it's a little less obvious that it approaches your limiting population, except that, of course, e to the negative KT is going to approach 0, so your denominator is going to approach A. So when you divide LA by something that approaches A, you're going to approach L. So either way, you have a solution. If you graph the solution, then depending on your initial conditions, Here's P equals L, population here, time here. Okay. Early on, e to the kt, well, that's going to involve a little more algebra than I want to get into. At the very beginning, t is close to 0. The denominator here is close to 1 plus a. Okay, so I am going to write some of this out. So your population is going to grow with a growth rate of L over 1 plus a times e to the kt. Meaning you're going to have some initial population here, and you're going to grow exponentially. Now, as you approach your limiting population, e to the negative kt plus a is going to approach a, and your population is going to asymptotically approach this. Of course, you can do phase diagrams and everything else, and we've done that earlier with equations like this. Okay, so you have this. I could say more, but you want to play around with it. Now, this is if P of 0 is less than L. If P of 0 is greater than L, then I'm going to have something like this. Again, this agrees with your phase portrait. You can also relate this to the graph of your Kp times L minus P. Rate of change of P equals this. It's a simple quadratic polynomial with zeros at P equals 0 and P equals L. You don't have negative populations, so you can simply sketch this like so. Now we do go beyond L because population can exceed L. You're into this range here. Okay, so there's your rate of change of population. And as we did when we looked at just general phase diagrams and so forth, this relates to the vector field. Now the word's escaping me. Diagram with the little segments for E. And I'm going to call it a phase diagram because I got that in my head. Direction field, okay, relates to your direction field and so forth. So all that should relate this equation back to what you already know and what you've already investigated. The algebra is as it is. It's not all that bad, but you got to get used to it. And I think you've pretty much done everything except maybe some of the algebra that goes in with this. If you know your initial population and so forth, you can evaluate K. Okay, so let's see if I can do this without dropping the board or having one jump off. You've seen mixture problems, and the applications are going to include mixture problems. And I'm just wanting to look ahead to I think the 3-2 the text when addresses the alien effect starts out with kind of a humorous statement. So you might enjoy that. Okay, and this, as we see, section 2. Oh yeah, section 2 does include the chemical reactions, mixture problems, and leaking containers. So what I want to do is I want to look at a leaking container. I don't think we've done this. We have done the cylinder container. Cylindrical container leaks. So we got water in it. The rate of outflow proportional to the square root of pressure as you know from Bernoulli's equation in physics. So it's proportional to the square root of y. Y equals 0 at the whole. So you have y dt equals k times the square root of y. And just reminding you, it follows after a few manipulations. Your depth changes, or your depth is a quadratic function of time for a cylindrical container. Now, conical container, let's just say you got a hole at the bottom here, so the water's flowing out of this hole. Again, you have something proportional to the square root of y, but what you have proportional to the square root of y is the volume of the container, because the rate at which fluid flows out of here depends only on how deep the water is, and you still have the same pressure relationship. And Bernoulli's equation still holds, and you might want to review that and how it's an expression of the conservation of energy and so forth. And now I have had the I think you can read everything. I hadn't switched back to the screen here, but I think you can see this, see the K square root of y right there. Yeah, it's going to work. Okay, so you have a cylindrical container, a conical container now. dV dt is K square root of y. Cross-sectional area at y is proportional I'll say to the square of the diameter at y, and diameter at y is proportional to y. And the proportionality constant here depends on the ratio of diameter at the top to the height at the top. I don't like to use D for variable because we're into differential equations and D has its own meaning. So I'm going to change diameter here. Should have had a little forethought. That's what I just said about diameter. Can be said about radius. Okay. So if the radius at the top and the height at the top are R and H, okay, and R of Y, meaning the radius at height Y, is radius at the top over height, because the radius at the top over height, or the diameter at the top over height, whichever what you want to look at, has the same proportionality at every height. So that the radius here is in proportion to the radius up here as this distance is to this distance. It's very straightforward geometric proportionality. So you have this. Then the radius at y equals this. So A sub CS, which is going to mean the cross-sectional area at R is pi times R of y squared equals pi times big R squared over H squared y squared. And there's the cross-sectional area. Then, if you know the rate at which volume is changing, the dV dt is equal to the cross-sectional area times dy dt, okay? And that's just, you multiply the area by a small change in the depth or the water level, and you get the volume, okay? Volume of something is very close to a cylindrical section. So yeah, by that geometry, you then say that dV dt is this times this, and ACS is proportional to y squared. So this is going to be y squared dy dt and I've written this wrong. No, I've written it right. Well, we're about to run out of time. I'm out of board space, and something doesn't seem quite right here, because dV dt never mind. So dy dt is proportional to reciprocal of cross-sectional area times dV dt times y squared. Well, I didn't have a y squared there. Okay, so y squared dy dt haven't written all that out correctly, but I'm going to say dy dt is going to be proportional with another proportionality constant to y to the negative 3/2. So you need to work through the geometry of this. Also write things down a little more carefully than I did. And we'll leave it at that. You can correct anything that needs to be corrected here because it still doesn't seem right and we're out of time. So I'm going to stop the recording right now. Maybe we'll reconcile this. You want to take another minute or two? Okay. Here we have the cylinder again. I need to get a little more detailed in my explanation of what's going on and how the change in volume relates to the change in depth. Okay, so here's your depth y. At this depth, you have a certain cross-sectional area, the area of the circle, and we have the expression for that because the radius of the circle is in the same proportion to y as the radius of the circle up here at the top is to the total height of the container. Now, if we have a small change in is equivalent to a change in volume is equal to cross-sectional area delta y. Sorry, Richard, you had?
What's that?
I heard you say something.
Oh.
But I'm going to assume that you were just fighting off the Huns or something and had them verbalize it a little bit. Not a problem. Okay, so we have this picture. Okay, so we have a thickness delta y here. So the volume is just the cross-sectional area times the altitude of your cylinder. If it's a small delta y, the cross-sectional area doesn't change.
I'm going to have to head back to work. So I'm going to have to drop off this video, but I'll watch the video once you upload it.
Okay, it's not going to take too much longer, so there'll be just a little bit. But
all right.
I kind of needed this picture to keep it straight. So, and hopefully it'll be helpful to you. Enjoy work. Give my regards to everybody.
I will. Thanks. See you Thursday.
Good, Richard. Okay, small delta y, cross-sectional area doesn't change significantly. And that justifies this. Thus, a small step to dv dt, the rate at which the velocity changes, is equal to cross-sectional area at y times y dt. So dy dt is reciprocal to cross-sectional area at y times dv dt. Cross-sectional area at y is proportional to y squared. and dV dt is proportional to square root of y, so that dy dt is proportional to 1 over y squared times the square root of y. And it is, as I said, but now we have a little more detail in why this works. Dy dt, then if dy dt is proportional to 1 over y squared square root of y, then dy dt equals k times the square root of y over y squared, which equals ky to the negative 3/2. Okay. So conceptually, dy dt or dv dt slows proportional to the square root of y. Okay, and that's the same as if you had a cylinder, uniform cylinder. Since in this case the area is rapidly, well, the area is decreasing proportional to the square of y, your dy dt changes even more slowly. Or I'm sorry, your dy dt changes more and more quickly as y decreases. Okay, because y to the negative 3/2, well, just in terms of the graph of square root of y versus y is going to be this. The graph of reciprocal of y and the graph of reciprocal of y to the 3/2. Well, there's 1 over y if you know these basic power functions. The graph of 1 over y squared going to be like this, much steeper as y approaches 0. And y to the 3/2 being halfway between y to the negative 3/2 being halfway between, being between y to the negative 1 and y to the negative 2, then your graph of y to the negative 3/2 is going to be somewhere in between these two. So somewhere around here. And you see that as y to 0, well, first of all, the smaller y is, the greater the value of this. So the greater the rate at which y changes. And as you approach 0, the rate of change approaches infinite. Now, in real terms, because of viscosity, adhesion, and so forth, you're not really going to approach that rapid of a change. So you're not going to have shock waves coming out of this thing. But that's just the physics of it. This is more about the model. And your book does the conical model also, probably doesn't go into quite as much detail. So I wanted you to have the detail so that you understand everything. Maybe not everything there is to understand about the model, but give you just a little more depth in your understanding, depth being different than the depth of the water. Okay.